Rocket propulsion, this is going to blow your mind, literally. So, some different types of rocket propulsion systems. They are all driven by an engine. We have propeller propulsion systems, which is not rocket, turbine, ramjet, and scramjet, and then rocket. So, we're going to look at rocket specifically now. Yay! It produces thrust by ejecting stored matter. And rockets can be classified by propulsion. You have liquid propulsion, you have solid propulsion, electric propulsion, which we're going to take a look at a little bit later. Some other classifications, you have expendable or reusable. There are a different number of stages. So this would be something that you would want to note in your notes on rocket propulsion. And again, there are other options that we're going to look at as far as different classifications, but liquid and solid are a couple of the biggest ones. And then classifications can be size of payload. Finally, manned or unmanned. So right now we have some fuel and oxygen and heat, and they explode, and then you have heat as a result. And then there's exhaust, and the exhaust is actually what's propelling you. Then that heat goes by back here, and it's kind of helps with the fuel and oxygen to form more combustion explosions. All right, so let's look at a liquid fuel rocket. A liquid fuel rocket here, fuel is up on the top here. You have an oxidizer here, your oxygen, and then you have pumps to apply them at the exact same appropriate amount. Then you use your combustion chamber, and then it goes down the throat. And then out the nozzle. So here's your nozzle area, which is really important because that helps you figure out what the thrust is. So we're going to take a look at this thrust equation in just a second. You do not need to write this equation down yet, but knowing that a liquid rocket is going to have a fuel and an oxidizer and pumps, probably pretty important. So your fuel is mixed with oxidizer, it's burned, gas escapes. And then let's look at solid fuel rockets. So this one is different, so you might want to draw this one just to have a point of comparison. You have all of your propellant mixture is this solid chunk here, and then this is the combustion chamber, and usually it's in some sort of a shape. And like looking from this edge, looking from the nozzle up, it's going to form some sort of a shape. So looking into this, this might be a circle, in which case three-dimensionally this is like a cone coming into here. That shape can vary, and depending on how fast you want something to burn will depend on that shape there. So your flame front is this yellow area. That's the part that's combusting. It's burning away this material, and it's oxidizing with just the oxygen that is set around this thing. And then it's combusting here and then exploding out the back. So it's burned to generate gases, it escapes out the nozzle to generate thrust, exactly the same. This, do not write all this down, I'm just going to explain a little bit about this. Mass flow rate can be defined in this way, and we'll get to that in just a little bit, but sort of the things that I'd like you to focus on here, because again, these are all equations for all sorts of different pieces of our thrust in this case. It's really this last thrust equation. But before we do that, I want you to look at the exit velocity is a significant component, that VE. Your exit pressure, PE, right here, the exit pressure versus PT, and that's the total pressure at the beginning here. And then exit temperature versus the total temperature. Those are the things that we're comparing. We're comparing the beginning here to how we exit. So let's move on. You still haven't written anything down yet, and now you can write this thrust equation down. Let's take a look at it. So two forces that act together to create rocket thrust. It's mass ejection and expansion of the gas. So let me explain each one of these two components that we're adding together to get thrust. First, consider gases that change from pressure P initial, that's P0, to P exit. So your initial pressure, whatever it is, and your exit pressure. So if your exit pressure is a higher value, then this is going to be a positive number. So the greater differential you can have here, the greater value that you're adding to your thrust. Pressure is force over area. So the resulting force in the rocket is proportional to the pressure differential times the nozzle area. So a bigger nozzle area and a bigger pressure differential gives you a larger thrust, a larger force exiting here. Now let's look at this component here. The gas is flowing out with a mass flow rate of m mass flow rate, m dot here, and velocity, exit velocity here. Now momentum, let's go back a step. Momentum of a gas, remember from physics, momentum is just mass times velocity. Force is proportional to the rate of change of momentum. So now let's go from physics into calculus, which some of you have taken, some of you haven't. In calculus, if you're going to find the rate of something, you take the derivative of it. So it results in a force for mass ejection given by the derivative with respect to time of momentum. And that gives you a mass flow rate. That's this m dot. So you don't need to necessarily know the calculus behind it, but just know that m dot is mass flow rate. It's the rate at which the mass is flowing, the mass of the gases is leaving, times the exit velocity of them. Now let's look at specific impulse. So specific impulse, you're not writing any of this stuff down either. We have the rocket thrust equation. We just kind of talked through that piece here. It has an equivalent velocity here, so you can calculate force by mass flow rate times v equivalent. And here we have a total impulse equation. Impulse equals force times a change in time, which you may also know from your physics class. And then specific impulse, this is what we're going to take a look at. Specific impulse is force divided by mass flow rate times initial gravity. And it's initial gravity because when you leave Earth's atmosphere, gravity value is going to be changing. So things that I would like you to write down are total impulse, I equals F delta T. Make sure you write that down. And specific impulse equals total impulse divided by the weight. So please note that. And then this equation. And that's a capital I with a little tiny lowercase sp, kind of like that. ISP equals force divided by mass flow rate times initial gravity. Now, this is where we're going to use this. The value for impulse is the integral of force with respect to time. And so thrust force is a function of time. If you plot the thrust as a function of time, you can integrate the values to find the area under the curve. So when we thrust our rockets, the total area under this thrust versus time curve is the total impulse. And Logger Pro will integrate this for you. So you don't need to know calculus. It will all be done for you. What we are going to do, though, is we're going to hook a force sensor up to our rocket, and it's going to should show the initial impulse here, and then we have our initial thrust right here, and then we have a sustained thrust, and then it drops off. And that total area underneath here is our total impulse. So that's kind of a really important piece there, that the area underneath this thrust curve is the impulse. Write that down 7 times. Here's what's going to happen with our model rocket. We launch it, it has a power descent, and then it is coasting, but see, it's still going up as it's coasting. Write that down. You still go up after your rocket engine turns off. When your rocket turns off, it doesn't just go, it goes up continually because it's got momentum. So it still goes, coast, and then there's a time delay for the rocket engine. That time delay then will pop the other direction of the rocket engine, will pop the top off, and then hopefully you have a parachute on it, and then you can recover it. So that's sort of how it's designed. Here's a little picture of it. You might want to draw this and sort of note these things too. Your ceramic nozzle, remember ceramic is a very high temperature, protected from your research and engine designs. Here's your solid propellant, and this is the combustion area. So this is the high thrust right in here. This is delay, so it burns through this, but it's not actually thrusting during this spot. So here's your power descent. This is delay, it's burning through it, it's not providing any thrust. That's the dotted part. Then you have a little ejection charge, one more solid fuel propellant charge here. It sparks this and it pops the clay retainer cap out the top, and that pops the parachute out. So this is kind of another little picture of it. And you're going to end up with a rocket, one of these rockets, A, B, which we're going to be A and B that we're going to test. And this gives you the actual impulse value that you're supposed to get. So if we have a B64, then this is the impulse code. B is the impulse code. This is the thrust, 6 newtons of thrust, and a 4-second delay. So after the thrust is gone, 1, 2, 3, 4, then the clay pops out, and then your parachute comes. So note this. This is important to know how to read these actual rocket engines. And here's a big chart that kind of helps you read them. Once you get your engine, you'll find it on the chart. If you have a C65, we have an impulse of 10, time delay of 5 seconds, and it also gives you your max lift, max thrust, thrust duration, initial weight, and propellant weight. So you have kind of an idea of the size of rocket that you could build if you wanted to make your own custom rocket. And this is the graph of what you might find. You have the total impulse here. Here's your delay period. You can see the graph is cut right here because there's a long delay, and then the ejection charge activates. So when we graph this, we should see a graph like this, quite a bit of a delay, and then a little pop spike right at the end. Let's do it.